question at hand involves differing opinions on whether installing ground detectors on ungrounded delta systems, specifically 480-volt systems, using a WIE transformer and power resistor to derive and neutral subjects the system to National Electrical Code, or NEC, section 250.36. Some argue that the system remains ungrounded because the instrument is solely for ground detection. Let's delve into the arguments for both sides, ungrounded and grounded, as well as relevant standards. First, let's consider the arguments for classifying the system as ungrounded. The NEC defines an ungrounded system in Article 100 as an electrical distribution system where there is no connection between the system conductors and either the earth or the equipment grounding conductor, except through capacitors or other series devices. Proponents of the ungrounded classification argue that the use of a WIE transformer and power resistor to derive a neutral does not create a grounding conductor because the neutral point of the transformer is not connected to the system conductors or to earth directly. Secondly, it is argued that the ground detectors are installed solely to indicate the presence of a ground fault and do not provide a path for ground current to flow under normal circumstances. Now let's examine the arguments for classifying the system as grounded. NEC section 250.36 requires that a transformer resistor grounding device be installed on ungrounded delta systems over 300 volts between phases. Those who argue for the grounded classification point out that the WIE transformer provides a neutral point reference that is grounded by the power resistor. This creates a path for ground current to flow, albeit a high resistance path. Concerns about electrical safety also arise, as high resistance grounding systems can introduce safety risks such as high touch voltages and step potentials during ground faults. Supporting this classification, IEEE Standard 141-1993 Recommended Practice for Electric Power Distribution for Industrial Plants, section 5.12 states that the purpose of a grounding resistor in a resistance grounded system is to intentionally provide a current path for ground fault current. In addition, a neutral is created and made available for instrumentation and relaying purposes. Also relevant is IEC 60364-4-41. Electrical installations for buildings Part 4-41 Protection for Safety Protective Measures Against Electric Shock, Section 413.1 1.2 states that resistance earthing is a type of earthing in which a neutral point or the exposed conductive part of an installation is connected to earth through resistors or other nonlinear devices. Therefore, based on these points, it is important to understand some of the key elements to determine if the system is grounded or ungrounded. Firstly, the NEC definition of an ungrounded system states there is no connection between the system conductors and either the earth or the equipment grounding conductor. Secondly, the use of a WIE transformer and power resistor to derive a neutral does not create a grounding conductor. The neutral point of the transformer is not directly connected to the system conductors or earth. Thirdly, ground detectors are there to indicate a ground fault, but do not provide a ground current path. On the other hand, arguments for a grounded system include that the NEC section 250.36 requires a transformer resistor grounding device be installed on ungrounded delta systems over 300 volts. In addition, the WIE transformer provides a neutral point reference that is grounded by the power resistor, which creates a path for ground current to flow, albeit a high resistance path. There are electrical safety concerns with high resistance grounding systems. IEEE Standard 141-1993, Section 5.12 states that the purpose of a grounding resistor in a resistance grounded system is to intentionally provide a current path for ground fault current, and also a neutral is created for instrumentation. The IEC 60364-4-41 Section 413.1 1.2 states that resistance earthing is a type of earthing in which a neutral point or the exposed conductive part of an installation is connected to earth through resistors. Therefore, the evidence and industry standards support that high resistance grounding of low voltage delta systems using WIE transformers and power resistors falls under the requirements of NEC section 250.36, and these systems should be treated as grounded systems for safety purposes. Now let's delve deeper into the NEC requirements and IEEE standards to clarify the requirements and recommendations for high resistance grounded systems. The NEC provides specific guidelines for grounding electrical systems to ensure safety and proper operation. Section 250 covers grounding and bonding requirements, including those for grounded and ungrounded systems. For high-resistance grounded systems, Section 250.36 outlines the requirements for grounding impedance, ground fault detection, and overvoltage protection. According to the NEC, high-resistance grounding is permitted for systems where continuity of service is essential, and where the maximum ground fault current is limited to a low value to reduce equipment damage and voltage rise during ground faults. The grounding impedance, typically a resistor, is connected between the system neutral point and ground. The resistor limits the ground fault current to a predetermined level, usually a few amperes. This limited current prevents severe equipment damage and reduces the risk of arc flash hazards. Furthermore, the NEC requires ground fault detection to be installed on high-resistance grounded systems to quickly identify and isolate ground faults. Ground fault detectors monitor the current flowing through the grounding resistor and activate an alarm or trip the circuit when a ground fault is detected. This allows for prompt action to be taken to locate and clear the fault, minimizing downtime and ensuring the safety of personnel. IEEE Standard 141, also known as the Red Book, provides recommended practices for electric power distribution in industrial plants. Section 5.12 specifically addresses resistance grounding and offers guidance on the selection and application of grounding resistors. The Red Book emphasizes that the primary purpose of a grounding resistor is to intentionally provide a current path for ground fault current. By limiting the ground fault current, the grounding resistor reduces the magnitude of fault currents, which can prevent equipment damage, minimize voltage dips, and improve system stability. The IEEE standard also highlights the importance of selecting the appropriate grounding resistor value based on system parameters such as voltage, available fault current, and desired ground fault current limit. Proper coordination of the grounding resistor with ground fault protection devices is essential to ensure effective fault clearing and system protection. High-resistance grounding offers several advantages over other grounding methods, such as solid grounding and ungrounded systems. In solid grounding, the system neutral is directly connected to ground, resulting in high ground fault currents during ground faults. These high currents can cause significant equipment damage, voltage dips, and arc flash hazards. High-resistance grounding, on the other hand, limits the ground fault current to a low value, reducing these risks. In ungrounded systems, there is no intentional connection between the system neutral and ground. While ungrounded systems can continue to operate during a single ground fault, they are susceptible to transient overvoltages, which can damage equipment and pose a safety hazard. High-resistance grounding provides a controlled path for ground fault current, mitigating the risk of overvoltages and allowing for ground fault detection. However, high-resistance grounding also has some limitations. It is not suitable for systems where ground fault current is required to be high for fast fault clearing, such as in some utility distribution systems. Additionally, high-resistance grounding can introduce challenges in locating ground faults, as the limited fault current may make it difficult to pinpoint the fault location. Despite these limitations, high-resistance grounding is widely used in industrial plants, commercial buildings, and other facilities where continuity of service is critical and where the benefits of reduced fault currents and improved safety outweigh the drawbacks. In summary, the classification of high-resistance grounded delta systems using WYE transformers and power resistors is a complex issue with arguments for both grounded and ungrounded system classifications. However, the weight of evidence and industry standards, including NEC Section 250.36 and IEEE Standard 141, support the argument that these systems should be treated as grounded systems for safety purposes. By adhering to the requirements and recommendations outlined in these standards, engineers and electricians can ensure the safe and reliable operation of high-resistance grounded electrical systems. Now let's explore some practical considerations for implementing and maintaining high-resistance grounded systems. Proper installation and maintenance are crucial for ensuring the effectiveness and reliability of high-resistance grounding. Here are some key considerations. Firstly, grounding resistor selection. Choose a grounding resistor with an appropriate resistance value based on system voltage, available fault current, and desired ground fault current limit. Consider factors such as continuous current rating, short time overload capacity, and insulation class. Secondly, grounding resistor location. Install the grounding resistor as close as possible to the system neutral point to minimize impedance and voltage drop. Ensure that the resistor is properly ventilated to prevent overheating. Thirdly, ground fault detection. Install ground fault detectors that are sensitive to the limited ground fault current of the high-resistance grounded system. Use detectors with adjustable settings to optimize sensitivity and avoid nuisance tripping. Fourthly, wiring practices. Use appropriately sized conductors for grounding connections to ensure adequate ampacity and minimize impedance. Follow NEC guidelines for grounding electrode conductor size and installation. Fifthly, periodic testing. Conduct periodic testing of the grounding system to verify the integrity of grounding connections and the proper functioning of ground fault detectors. Use test equipment designed for high-resistance grounded systems to simulate ground faults and measure fault currents. Sixthly, documentation. Maintain detailed documentation of the grounding system, including grounding resistor specifications, ground fault detector settings, and test results. Keep the documentation readily available for reference during maintenance and troubleshooting. Seventhly, training. Provide training to personnel on the principles of high-resistance grounding, ground fault detection, and safe work practices. Ensure that personnel understand the importance of maintaining the grounding system and responding promptly to ground fault alarms. High-resistance grounding is often used in conjunction with other protective measures to enhance electrical safety and reliability. For example, surge protective devices can be installed to protect equipment from transient overvoltages caused by lightning strikes or switching surges. Additionally, overcurrent protection devices such as circuit breakers and fuses can be used to protect equipment from overload and short-circuit conditions. Coordination of these protective devices with the grounding system is essential to ensure proper operation and minimize the risk of equipment damage. In addition to the NEC and IEEE standards, other industry standards and guidelines may provide valuable information on high-resistance grounding. For example, the International Electrotechnical Commission, or IEEE, publishes standards for electrical installations, including those for resistance earthing. Consulting these standards can provide additional insights into best practices for grounding and protection of electrical systems. Furthermore, it is essential to stay up to date with the latest revisions of the NEC and IEEE standards, as these standards are periodically updated to reflect new technologies, changing industry practices, and lessons learned from field experience. By staying informed and following the latest standards, engineers and electricians can ensure that high-resistance grounded systems are designed, installed, and maintained in accordance with the best available knowledge and practices. In conclusion, high-resistance grounding is a valuable technique for enhancing electrical safety and reliability in a variety of applications. By limiting ground fault currents, high-resistance grounding reduces the risk of equipment damage, voltage dips, and arc flash hazards. Proper implementation and maintenance of high-resistance grounded systems require careful attention to grounding resistor selection, ground fault detection, wiring practices, and periodic testing. Consulting industry standards and guidelines such as the NEC, IEEE standards, and IEC standards can provide valuable information on best practices for high-resistance grounding. By following these practices, engineers and electricians can ensure the safe and reliable operation of high-resistance grounded electrical systems. Now let's address some frequently asked questions about high-resistance grounding to further clarify its principles and applications. Firstly, what is the purpose of a grounding resistor in a high-resistance grounded system? The grounding resistor limits the ground fault current to a predetermined level, typically a few amperes. This reduces the risk of equipment damage, voltage dips, and arc flash hazards during ground faults. Secondly, how is the resistance value of the grounding resistor determined? The resistance value is selected based on system voltage, available fault current, and desired ground fault current limit. IEEE Standard 141 provides guidance on selecting the appropriate resistance value. Thirdly, what type of ground fault detectors are used in high resistance grounded systems? Ground fault detectors that are sensitive to the limited ground fault current are used. These detectors typically monitor the current flowing through the grounding resistor and activate an alarm or trip the circuit when a ground fault is detected. Fourthly, can a high resistance grounded system continue to operate during a ground fault? Yes, a high resistance grounded system can often continue to operate during a single ground fault. The limited ground fault current does not typically cause severe equipment damage or voltage dips, allowing for continued operation until the fault can be located and cleared. Fifthly, what are the advantages of high resistance grounding compared to solid grounding? High resistance grounding reduces the magnitude of ground fault currents, which can prevent equipment damage, minimize voltage dips, and reduce the risk of arc flash hazards. Solid grounding, on the other hand, results in high ground fault currents that can cause significant damage and pose a safety risk. Sixthly, what are the advantages of high resistance grounding compared to ungrounded systems? High resistance grounding provides a controlled path for ground fault current, mitigating the risk of transient overvoltages that can occur in ungrounded systems. Additionally, high resistance grounding allows for ground fault detection, which is not possible in ungrounded systems. Seventhly, where is high resistance grounding commonly used? High resistance grounding is commonly used in industrial plants, commercial buildings, and other facilities where continuity of service is critical and where the benefits of reduced fault currents and improved safety outweigh the drawbacks. Eighthly, how often should high resistance grounded systems be tested? High resistance grounded systems should be tested periodically to verify the integrity of grounding connections and the proper functioning of ground fault detectors. The frequency of testing depends on the specific application and environmental conditions, but annual testing is generally recommended. Ninthly, what are some common problems associated with high resistance grounding? Common problems include improper grounding resistor selection, inadequate ground fault detection, and poor wiring practices. Regular inspection and maintenance can help prevent these problems. Tenthly, what are the safety precautions that should be taken when working on high resistance grounded systems? Personnel should be trained on the principles of high resistance grounding, ground fault detection, and safe work practices. Lockout/tagout procedures should be followed when working on electrical equipment, and appropriate personal protective equipment should be worn. In addition to these frequently asked questions, it is important to consider the specific requirements and recommendations of the NEC, IEEE standards, and other relevant industry standards when designing, installing, and maintaining high resistance grounded systems. Consulting with qualified electrical engineers and electricians can help ensure that these systems are implemented safely and effectively. By understanding the principles of high resistance grounding and following best practices, engineers and electricians can enhance electrical safety, improve system reliability, and minimize the risk of equipment damage in a variety of applications.